variability. We talked about lean layout, just in time, pull system, push system. Okay. So the material we are covering is very related to what we covered before in chapter 6 and chapter 12. So you remember the EOQ model we covered, which is this inventory model. And we said we place the order so our Q is at maximum here, then we use what we use and then we order again. Okay, so now we will use this equation, which is the EOQ, to calculate the setup time. Okay, so the ideal situation where we have lot size of one pulled from one process to the next one. So we can use the EOQ to calculate what we call the desired setup time. Okay, this will 2K changes necessary to improve the material handling and reduce. Our goal is to reduce the setup time. Okay. So this is an example here where we have a firm that produces furniture and they want to move toward the reduced lot size. So determined that a 2-hour production cycle would be acceptable between two departments. Further, she concluded that the setup time would be accommodated, the 2-hour cycle time should be achieved. Okay, let's see what's given here. We are using the same equation we used in chapter 2, the EOQ equation. That's what we are going to use. So we are given the annual demand, which is 400,000 units. Okay, the daily demand can be calculated. Okay, the daily demand, as we mentioned before, can be calculated by dividing the annual demand by the working days. So can somebody remind me what I said when we covered chapter 12? We said if we are not given the daily demand, we should use how much? You mentioned that before.
The annual.
Yeah, if the number of days, the working days is not given for this class, we just use the 250, okay?
Yeah.
So if I give you a question and the number of working days is not given, which is this 250, just use 250, okay? Okay, so when we are given the daily demand here, the annual demand, we divide by the number of days. This will give us the daily demand because you need the daily demand here, which is the small d. We said the small d refers to the daily demand. Here we are given the daily production rate, which is 4,000. It's already given. You know, before we used to know the cost, the setup cost. Now we need to find the setup cost. That's the only difference. So we are given the EOQ. Before we used to find the EOQ or the Q star based on the EOQ, okay? QP, which is given here 400. Holding cost is $20 per unit. Setup cost to be determined. So hourly labor rate, this is very important. We will need it at the end. Okay, so we rearrange the equation. So we have Q star P is 2ds over H1 minus D over P. If you square both sides, square this side and this side, so this will remove the square root, and this will be Q star square P, which is equal to 2ds times H1 minus D over P. And then you rearrange the equations, so at the end you will have S is equal to Q squared H1 minus D over P over 2 times the annual demand. Okay, so now let's plug in the numbers. 400 squared, 21 minus over 1600 divided by the 4000, which is the daily production rate, divided by 2 times 400,000. This will give us the sit-up cost, which is $2. Okay, 0.40. Okay, so now we need to convert this to hours. What does this equal? Okay, how to do that? We just divide it by the hourly rate, $30 in our case here. Okay, don't leave it in dollars because your goal is to determine the sit-up time. It should be in minutes or hours. Okay, so sit-up time is equal to 2.4 divided by $30, which is 0.08 hours. Multiply the 0.08 times 60 minutes. This will give you 4.8 minutes. Let me put that here. Oh, we got this here. We multiplied this times 60. That's how we got the 4.8 minutes. Any questions?
No, not for me.
Yeah, that's easy. You know, some of you, they say, oh, why we reduce the setup time? What's the goal? High setup cost encourage large lot sizes. You know, I remember we visited a facility long time ago. You know, the setup time was for one of the machines, like 18 hours. Okay, that time. And the problem with that machine, there is a furnace in the machine. It should reach a specific temperature, and it takes long time to reach that temperature based on the technology that they are using. So if they turn off the machine and they need it, they have to wait 18 hours. Okay. If they keep the machine running, so the furnace will be running all the time, and this will cost them thousands of dollars. So, you know, I remember we spent time to find out what's the best solution for them. You know, imagine that if you turn it off, when you need it, you have to wait like 2 days to heat up. Okay. If you keep it running, so it will be running all the time, this will cost you money at both sides, you know. So That's setup time. Reducing setup cost reduces lot size and reduces average inventory. Of course, setup time can be reduced through preparation prior shutdown and change over. If we look here at this example, initial setup time 90 minutes. Here, if we use separate setup into preparation and actual setup, doing as much as possible. Every situation has different like solution. Move material closer and improve material handling. This will introduce standardized and improved tooling, as we mentioned in 5S. These techniques can be used to reduce the setup time, but for some situations, you need to like do a separate study to reduce the setup time, as the example I gave. Schedules must be communicated inside and outside the organization. Kanban. Kanban used in full system. Okay, let's see what's Kanban. Kanban. Lean scheduling, better scheduling improves performance. We use Kanban. We'll study Kanban later. Communicate schedule, supply freeze part of the schedule, perform to schedule, seek one piece make and one piece move. These are like lean scheduling techniques. Eliminate waste, produce small lots, make each operation produce a perfect part. It's perfect part means like no waste, no defects. Okay, that's the meaning of that. And we mentioned that before. We said instead of having inspection stations in the facility, we train our workers or operators to do it right first time. So make each operator or worker as an inspector, so you don't need to have inspections. Process frequent small batches rather than large batches. That's easier. Make and move small lots, so level schedule economical. This is just in a time. Look here, small batches. It's easier, okay, to control than large batches. Kanban, that's Kanban. It is a Japanese word for card. The card is an authorization for the next container of material to be produced. A sequence of Kanbans pulls material through the process. Many different sorts of signal are used, but the system is still called Kanban. So we have here an example, simple example you are familiar with is like the drive-through. Look at the drive-through here. So when you first arrive at the drive-through, you place your order, they have a computer or machine where you or a human talk to you. You place your order, and then they tell you to go to the next window to make the payment. So as soon, it's like just in time, okay? Well, the idea here, even using the computer or cards before they used to use cards. As soon as you place the order, they start making it, and then you pay, and then you move to the next window to receive your order. Signal marker hanging on post. For example, here you see for part. So the workers who work and use this material, they use flags like this. I don't know if any of you like visited the manufacturing facilities. So some facilities are huge and different machines. and the managers or the operations manager sitting like away. Okay, so there should be a way other than computers, signals by computers to see if one of the stations run out of material or raw material or parts. So they use Kanban. Signal marking hanging on a post for part Z405 shows that production should start for the part. The post is located so that the worker's normal location can see easily. Everybody can see that. Signal marker on stack of boxes, part number marks of location. So when they change this based on the inventory that they have. So if they are about to run out of the inventory, so the managers know, so they provide them with the required uh, parts. When there is a visual, that's called visual contact. That's the idea. The user removes the standard size container of parts from small, large area as shown. The signal at the storage area is seen by the producing department as authorization to replace the using department or storage area because there is an optimum lot size. The production or the producing department may make several containers at a time. This is here a sample. We call this a work cell. Okay, they make one part at a time. So it comes to this worker, or we call it like employee. He put something, it could be different method, like layout. Sometimes, now most of the time when you go to manufacturing facility, these people are replaced by conveyors and robots, but sometimes you cannot replace people with robots. It depends. I worked before in several projects where we replace people with robots. Of course, not always. Sometimes they save money. So let's say if you pay the worker like let's say $60,000 or $50,000 a year, let's say you pay the robot, but you have to spend lots of money to change everything. You need computers, you need conveyors, you need robots. You pay millions of dollars, but if the payback period is 2 or 3 years or 4 years, it's significant for them. Then they have the finished goods, and they after that they deliver the finished goods to the customer. When the producer and user are not in visual contact, a card can be used. That's the goal. Otherwise, a light, they use light. Of course, the manager, if he's sitting on his computer, probably on his computer, he should receive a signal that, oh, that's part Z is short now. We need to provide the line with more of that part. Usually, each card controls a specific quantity of parts, or multiple card system may be used if there are several components on the lot. Kanban cards provide direct, as we mentioned, and it depends on the situation. So the number of Kanbans here, the number of Kanbans or Kanban cards or containers. Need to know the lead time to produce a container of parts. Need to know the amount of safety stock needed. So number of Kanbans is calculated by this equation. We demand during lead time plus safety stock divided by the size of the container. So this formula used to calculate the number of Kanbans or Kanban containers. Okay, let's see example here. Let's look at this example. I keep moving this because I want to read. So this is Hop's Bakery produces short runs of cakes that are shipped to grocery stores. The owner wants to try to reduce inventory by changing to Kanbans. He has developed the following data and asked you to finish the project having determined they know the EOQ size, which is Q star P, is 250. We then determine the number of Kanbans. So we know the daily demand, 500 cakes. We know the lead time, okay, 2 days. Okay, we know the safety stock is 1/2 day. The container size is 250. So demand during lead time. So here you need to deal with parts. So the demand during lead time, which is this point here, this part, this is calculated by multiplying the number of days times, you cannot say 2 days. This is parts, this is parts. You cannot add days to parts. So you need to convert the demand during lead time to number of parts. When you say 2 days, so that means 2 days times 500 is 1,000 parts. Also the safety stock is given as half day, 1/2. What does it mean? 1/2 times 500 is 250. Then I add the 250 plus 1,000 divided by 250. So the number of Kanbans needed is 5. Okay? That's how we calculate the number of Kanbans. So the idea here, you need 5 Kanbans containers. Okay?
Yes, sir.
Okay. Another example here. So where did this go? Let's see this example. Bakery code, the owner Ken Hobbs wants to try to reduce the inventory by changing to a Kanban system. He's developed the following data and asked to finish the project. EOQ size is 250. So if the daily demand is 600 cakes, the production lead time is 3 days. What's the number of Kanbans here?
Say that again.
Yeah, you see this example, right?
Yes.
Okay. How much the lead time? 3 days, right?
Oh, you said how much lead time? I didn't get what you had said.
Yeah, the lead time is 3 days, right? 3 days times 600 is 1,800, right? So I put 1,800 here. Plus the safety stock is half day, 1/2. So it's 300. I divide that by 270. This will give me the number of Kanbans, okay? It's similar to the previous example. Advantages of Kanban: small containers require tight schedules, smooth operations, and this will reduce the variability. Of course, if we have shortage, this means we will not be able to satisfy the demand. And standardized contain reduce weight, the cost, space, and labor, of course. So lean quality, lean cuts the cost of obtaining goods quality because lean exposes poor quality, because lead times are shorter, quantity problems are exposed sooner. You know, if the lead time is short, so imagine that the lead time is 1 day. So if something happened and you don't receive the raw material, you will be in a big problem. So you will shut down the facility and for like 1 or 2 days. And that happens sometimes. Okay. You shut down the facility, that means you are losing money. So lean quality tactics use statistical process control as we covered in chapter 6. We know what's a process control. All these statistical process control, including the control charts, the CP and CPK, okay? Give authority to your employee, build fail-safe method like using Bokyuk. Let me see, I think I have a short video for this. Let me see if it is working. Escape verification. Yeah, this is just to give you an idea what we are learning here. We talked about Toyota production system, continuous improvement, respect for people. People are treated as knowledge worker. You know, when you work with others, you know, you need to respect their knowledge. Toyota production system process and standard where practices work shall be completely specified as to content, internal and external customer supplier material and service flow must be simple. It must be simple, you know. The process improvement must be made accordance with the scientific method. Okay. Jidoka, I think we talked about Jidoka, but Jidoka stopping production because of defect. Okay. So another example of Jidoka, like if you are driving car, for some cars, for example, if the engine oil is low, So some cars, they stop working. You cannot turn on the car. So I think I have another video for Jidoka. Let me see if we can watch that video. Okay, Jidoka.
This video right here ain't got no audio for me though. I'm just looking at bro lips move.
Me either.
What, you cannot hear?
No, this one we can't hear. No, it's just Brett talking, and I can't read lips that well.
Oh, okay. I will put the links on the class website. So let me see. So you can watch it. So this is our class here. What's this? Week 16. 16. And watch it when you have time. Of course, this will improve the process. You know, the lean organizations means understanding the customers and customer expectation, functional areas, communicate and collaborate to make sure that's the goal. You know, we want to make sure that we meet the customer expectations, what our customer expect from our product or service. Okay, all these lean and sustainability. It's another topic, two sides of the same coin. So in sustainability, we are trying to reduce the carbon footprint of a product or service and reduce the environmental impact of the material that we are using. Also, they share different things. Like, you know, in lean, we have reduce the waste. Effective part, that means, you know, we are saving natural resources, reducing energy use, water use, movement. That's exactly what sustainability means. Two sides of the same coin. Maximize, that's what we said. Resources use and economic efficiency. Focus and should outside the immediate, drive out waste. So we are talking about waste, including natural resources, defective parts, time. When we say natural resources, we mean like all natural resources, including the energy, water, and reduce the pollution also. The lean techniques used in manufacturing, as we said, and service. I have done several lean projects in hospitals. I used to, you know, you see here in this picture, when they do the surgery, they have lots of equipments around them, look here, tools. So these tools, maybe they are done with the surgery, but before they used to have